Buenos días con todos. Vamos a dar inicio a las ponencias. En esta oportunidad continúa una ponencia magistral con el PhD Stewart Williams. Él viene de la Universidad de Cambridge, de UK. El profesor Williams trabajó en la BAE System Advanced Technology Center durante casi 20 años antes de comenzar en la Universidad de Cranfield. El profesor Williams tiene el grado de bachiller en física y PhD en física de láser del Royal Holloway College en la Universidad de Londres, y sus actividades de investigación principales son enfocadas en la manufactura aditiva, usando el proceso de manufactura aditiva Wire plus Arc y en el proceso láser para usos de defensa y aeroespacial. Recibámoslo con un fuerte aplauso.
Thank you very much for the introduction. Buenos días, everybody. Thank the organisers for inviting me here. It's my first time in Peru, and it's certainly my first time in South America as well, so it's quite a treat. So I'm going to talk to you about additive manufacture using wire and arc, and I apologise for the title doesn't seem very fluent, but what we're going to do is give you a short introduction about the university itself. Just most people will not have heard about Cranfield University, and then talk about wire-based additive manufacture research at Cranfield. We've been doing this since the 1990s, actually, so with a lot of experience now in building complicated parts. And I'll finish by saying a little bit about what the challenges are going forward and what we expect to do over the next few years as well. So the university itself is originally an aircraft base. We have our own airfield, and it's entirely postgraduate with around 4,500 students. We produce the largest number of engineering graduates of any UK university, and the research we do is very highly focused on industrial applications. So because of that, we have the highest industrial income per capita of any UK university. The centre itself is the Welding, Engineering and Laser Processing Centre, and we have about 6 academic staff, 10 research staff, and around about 20-odd students, so around about 50 people. I might point out as well, it was founded in 1961, so we've been around a long time. In terms of facilities, we have a very large lab. It's the big green box that you can see circled there. And we have a lot of laser systems and arc welding systems and manipulators. And because we've been around for such a long time, we have more than 600 alumni in the welding field, and we frequently bump into our old alumni working as welding engineers, which is very refreshing, I must say. So, as I mentioned, we started this work back in the 1990s, actually, before additive manufacture was fashionable, and we developed what was then called a process called shape metal deposition. This was for Rolls-Royce, and the basic concept was that you built up parts out of depositing layers of weld metal using a robot. So this is one of the early parts that you can see here. This is Inconel 718, took nearly 3 hours to deposit, and you can see that we had a change in shape. And because it was working for Rolls-Royce, which is obviously an aircraft manufacturing company, a lot of the parts that we made were rather simple round structures, and you can see some examples here. And in fact, as I mentioned, it was developed for Rolls-Royce, and it was taken forward into full production and is still used today for making flying parts. And it's been very successful, although not adapted to these kind of complicated structures that I'm showing you here. So what have we been doing since then? Well, the motivation changed. So originally we were working, as I said, for aero engines, but now the focus is very much on aerospace airframe applications and oil and gas applications. So why has this change occurred? Well, if we look at the material usage in a 747 aircraft, you can see that 83% of it is aluminium. If we then go to the 777, you can see that the aluminium percentage has now dropped to 68%, And by the time we get to the 787, there's only 20% aluminium remaining on the aircraft, and 50% of it is carbon fiber composite. And the reason for the change in the aluminium usage is aluminium is incompatible with carbon fiber composite. So any remaining aluminium had to be changed to titanium. And you can see the amount of titanium has increased fourfold on a typical civil aircraft today. Now, the normal manufacturing method for integral metallic parts in aircraft structures is to machine them out of solid blocks of metal. This was okay in aluminium, it's relatively cheap, and it's also easy to machine. When they changed to titanium, they found actually this stuff's really expensive. It's 10 times more expensive, and it's very difficult to machine. It's 10 times harder to machine. So on a typical 787, they have round about $30 million of forgings in titanium. And they make a loss on every aircraft at the moment, so they want to reduce the cost of the manufacturing process, and the obvious target is these titanium forgings. So this was the main motivation for why we started this work. So before explaining a bit about what we do ourselves, I want to just highlight really some of the other processes that could be used for metal additive manufacture and explain why we work in the particular area that we work in. So when you're considering a metal additive manufacture process, you first of all have to consider whether you're going to use a beam or an arc as the heat source. And so once you've done that, you then, if it's a beam, you need to decide if it's a laser or if it's going to be an electron beam. If you're going to use an arc, of course, there are a range of different arc processes, such as TIG and MIG and MAG and plasma. And if you're Norse titanium, they use a dual plasma system. So that's the first choice, what kind of heat source are you going to utilize? Next, you need to decide whether you're going to feed the metal in the form of a wire or a powder. So we work exclusively on wires. There are lots of good reasons for that. We heard about some of the difficulties of powders this morning. Wires are readily available in high quality form, and there are much less safety issues. And most importantly, when you use it in an additive manufacture process, all of the wire is used. You don't use some fraction of the wire and have a remaining part which you then have to process somehow. So at Cranfield, we focused on two areas, which is the wire and arc system, which is what I'll talk about mostly today, and then also wire and laser, which also has some benefits. So we're often asked, we have a lot of industry partners in our program, and they always want to know, there are lots of different metal additive processes, as we just saw, which process should they use? So I use these diagrams to explain this to them and to explain why we operate in the region that we do. So for a single axisymmetric energy source, the build rate depends on the square of the layer height. This is just basic physics, and this applies to whether you have powder bed, blown powder, wire and arc, or anything. If you increase the layer height, you square, the build rate goes as the square of the layer height. And you can then plot on this diagram the different kind of processes. So you first of all have the powder bed, you then have the laser blown powder systems, and then you have the wire and arc additive manufacture, and then finally we have the high deposition rate wire systems, which is the electron beam freeform or the dual plasma system of Norse titanium. Okay, that looks pretty simple. So why wouldn't you use the very high build rate process? Obviously that's going to give you the lowest cost and the highest production rate. Well, unfortunately, the resolution also depends on the layer height. So as you increase the layer height, the minimum feature size or resolution increases linearly with the layer height. So if you put it down faster, then you put it down effectively less accurately. And we tend to operate in this region here. So we typically have a layer height of around 1 to 2 millimeters, and this gives us a resolution of around about 2 millimeters. And the reason why we select that point is because all of our parts at the moment are machined afterwards, and the optimum amount of material to be machined away is around about 1 millimeter. So given that you want to machine on both sides, this means the minimum resolution required is about 2 millimeters, or maybe 3. So we like to operate in this green region. And actually there's a third reason as well, which I'll explain in a moment. The other effect of increase in the layer height is you change the surface roughness. So the layer height, the surface roughness or surface topology also depends linearly on the layer height. So if you go for a higher layer height, you end up with a rougher surface and more material to machine away, and you're less close to net shape manufacture. But of course, one of the questions we always get asked is, why don't you do it faster? And of course, you could do it faster. It's very easy to have lots of arc sources and chuck in lots of material. But actually, if you look at the economics, and we spent a lot of time looking at the economics of these processes, the specific cost in pounds per kilogram of depositing the material initially decreases very quickly. So if you have a powder bed system, it's very attractive to go much more quickly. But you can see that the line asymptotically approaches a value, asymptotically approaches a value, which is the cost of the material. Eventually, if you start putting down the material very fast, all of the cost is in buying the material. There's no cost in running your machine. So it ends up that actually going faster doesn't save you any money. And you lose resolution, as I explained before. So the graph on the right shows how close you get to the buy to fly ratio. So this is how close to net shape you get. And you can see once you start increasing the build rate, you quickly depart away from having a low buy to fly ratio. So if you look at something like the electron beam freeform system or the Sayaki system or the Norsk system, they typically deposit at around about 6 to 7 kilos an hour, but their buy to fly ratio, the minimum buy to fly ratio, is about 4 or 5. So this means you've still got to buy 4 times as much material as you need. You've then got to deposit that material, and then you have to machine it away again. So you can quickly see that the actual cost of the part follows the sum of these two curves, and we end up with a sweet spot where you get the minimum cost saving. And if you're targeting cost savings, which is what we are doing, this is the area in which you want to operate. So going back to, so that's a sort of a background about why we do what we do in the particular region that we operate. So the main business drivers for the wire and arc additive manufacture is cost and material saving compared to the current manufacturing methods. And that's the current manufacturing methods of machining from solid blocks or machining from forgings. And I've put in a couple of examples there. The one on the left is a titanium wing frame structure. The one on the right is a landing gear rib for a small commercial aircraft. You can see that the buy to fly ratio of the rib on the right is 12. So the final part weight is 20 kilos. So this means that the starting block of metal they use is 240 kilos. So this is incredibly expensive and wasteful. So we end up that the manufacturing cost is £16,000. When we produce this part using WAM plus final machining, the cost saving is round about 70%. So this is a huge number, of course, and it's very easy to sell this to companies about reducing cost of their manufacturing process. Furthermore, we have greatly reduced lead times. So if you're going to use a forging, typically it's going to be many months before you can get the forging, or many years even. Because we can manufacture this within a few weeks, we're reducing the lead time for the components down from years to weeks. So we have cost and lead time savings. And of course, we want to apply it to large engineering structures because this is where the big benefit is. But we shouldn't forget that actually we can introduce new functionality into components as well. We haven't spent a lot of time looking at this at the moment because we're focused on the low-hanging fruit of the cost and lead time savings. So to satisfy this requirement, we then did a detailed study of wire and arc additive using new technology, so moving away from the SMD process to using other processes, and of course we've got much better control, we have much better systems and so on. So this is the first part we built, and this was back in 2006. So this was built with a process called cold metal transfer. and you can see it looks pretty good. It's a very simple steel part, and the cost of manufacture, actually, if you ignore the cost of the system, was £5. And it took 3 hours to build, and you can see that it's pretty accurate. We have a height variation of 200 microns and a width variation of 200 microns and a similar surface roughness. So actually, a lot of people think this looks pretty easy. Let's go and get a welder, a robot, and put them together and start building parts. Well, actually, it's very much more difficult than that, as people will find out. So we then needed to build parts with a bit more complexity than this. So we looked at different materials, carbon steel, aluminium, looked at how to do intersections, crossovers, and various other features that would be required in a real structure. And we also investigated what kind of build angles could you use. There's no particular reason why you need to build downhand. So you can see here we build at 60 degrees, 30 degrees, and horizontally. And this means, in fact, you can make enclosed structures without actually moving the part. So it's actually pretty flexible. I mean, a normal welding engineer would not be surprised by this because, of course, we weld in all positions. But if you talk to the additive manufacture community, they are very surprised by this. And we can make internal structures. So this is an example of making conformal channels into tooling structures. This is for something like composite tooling, where you want to improve the cooling rate or heating rate of the structure and make it more uniform. Similarly, for the automotive sector, this is for heat exchangers on press forming tools. So you would make your large 3D part with this structure on the top, so you could achieve rapid cooling when you carry out your press forming process. The biggest challenge by far in any DDAM process is controlling the geometry, the bead geometry. And unless you fully understand about how to do this, you will not make successful parts. And this step is usually avoided by most people. They just use a single set of parameters, and when they're trying to build parts, they inevitably have holes in them. So this is a process map for plasma deposition of titanium. The graph on the top shows you the wall width as a function of the wire feed speed and the current, and the graph on the bottom shows the layer height as a function of the wire speed and the current. So this would be a full baseline algorithm to allow you to change. You can see on the plot on the right, we can select a wall width, say between 6 and 9 millimeters. So we pick 8 millimeters, then we might pick a layer height of 1.2 millimeters. Now, when you're building additive manufacture parts using DDAM, the layer height is never what you want it to be. It always changes and it varies around the part. So you have to correct this every layer. And the only way you can do that is if you have a full detailed algorithm. So if the layer height ends up being 1.1 millimeters, on the next layer you build it with 0.9 millimeters. What about the different kinds of materials? Well, pretty much if you can get welding wire, you can deposit it. So, of course, the focus for us has been on the titanium because that was what the funding was for mainly. So we've looked at commercially pure titanium, standard 6.4, low oxygen and high oxygen 6.4 actually, 5553, which is a higher strength beta alloy, and also 407, which is a higher toughness material but lower strength. One of the things that we're trying to educate people to do, and as Steve mentioned this morning, the properties of what you deposit are nothing like the properties of a raw material. They're very different. So we're actually trying to persuade people to ask for properties and not ask for materials, because the material they get is not what they've asked for. It might have the same chemical composition, but it for sure is not the same material. For aluminium alloys, we've looked at a range of 2000 series, 2024, 2319, 205, some 5000 series, 5087, Safra 66 is 5566, and also aluminium silicon. Of course, aluminium alloys are much more challenging than titanium alloys because they are heat treatable, or most of them are, the high strength ones. So, for example, the 2024, if you want to get that in high performance, you need to do a solution treatment and artificial aging after you've deposited the material. And this is very difficult actually, because you've now got to treat a whole part, and there are going to be lots of issues around quench cracking and distortion, as well as getting uniform quench rates. In terms of steels, so these are mainly for the oil and gas sector, and we've looked at ER 60, 70 as well actually, 80, 90, 120, different kinds of maraging steel and also stainless steels. We've done Invar and the primary Inconel alloys of 625 and 718. So as well as these primary structural materials, we've also looked at different kinds of special metals, if you like. So the refractory metals, tungsten, molybdenum and tantalum, and then some copper and magnesium and bronze. And really there's no particular reason why you can't do any materials, as long as you can get the wire. So as an example, this is the video on the left is showing tungsten deposition. So we were told, this is using TIG deposition actually, and we were told by the laser powder people that we'd never do tungsten deposition with an arc because we couldn't get it hot enough. As you can see, we have a very nice stable process with continuous metal transfer, and we were able to produce very large structures completely free from pores. Just an example of some of the other more difficult materials. This is magnesium deposition. Of course, this is a big challenge. It has a very low melting point, but it also has a very low vaporization point. So there's a very narrow process window whereby you either don't melt it or you vaporize everything. So actually getting the right conditions is quite hard for that. This is copper silver. So this is very high electrical conductivity copper, and when we deposit the material, you can see from the macrograph it's 100% dense. This is all as deposited. We don't do any hipping or any subsequent processing. And we achieved the 102% of the conductivity of pure copper. In terms of controlling the properties, we can look at other combinations. So in this case, we're using a wire and a powder. So in the picture on the left, you can see on the left-hand side, we're feeding the wire in. On the right-hand side, we feed the powder in. And in this case, we put down a steel tungsten carbide metal matrix composite. And of course, again, you can do different combinations of these. If you want to change the composition, one of the challenges is getting new wires. So wires are designed for welding. They're not designed for additive manufacture. So the way we go about that is to use a multi-wire approach. So in this case, we're using two wires feeding, one is an aluminium copper wire, one is an aluminium magnesium wire. We can feed them in at different rates, and you can see from the diagram on the right, we can continuously vary the ratio of magnesium to copper in the deposited material, and then we can test the properties. And this is the point I was making earlier about asking people, what properties do you require? Tell us what the properties are, and then we'll come back and deposit the suitable material for you. And in fact, you can take that further as well. So this is using 3 wires. So because the aluminium copper wire is limited to 6%, if we want to get the copper higher than that, then we would use a 3rd wire. And in this case, we achieved 8%. And you can see the increase in hardness. Because we're using wires, it's very straightforward to swap between materials as long as they're metallurgically compatible. So in this case, we swap between steel and copper. And in this case, we swap between Invar and steel. And these changes in different materials and making mixed material structures is certainly will be a big area of research in the future. And we can make a graded structure. So in this case, this is we started off with tantalum, then we go through molybdenum to tungsten. So this is, of course, is for nuclear applications for the plasma screening systems, but nicely demonstrates how we can swap. So tungsten doesn't have very good mechanical properties, whereas tantalum does. So we put down this graded structure, and then we can make an area that has high neutron screening, but attached to a substrate that has high mechanical properties. Another factor that we introduced to improve the mechanical properties was to introduce cold work. So this is a process that we patented, whereby we deposit a layer, we then cold work this layer using a roller in this case. We then put down another layer which thermally treats the cold work material. And as was mentioned earlier, if you don't do anything in terms of titanium deposition, you get these large columnar pi beta grains. you get a very anisotropic structure which is highly textured. When we introduce the rolling process, you can see that we get a very fine equiax microstructure. We now have no texture, it's completely isotropic, and we also change the size of the alpha laths so that we get much better properties overall. And you can see this in this diagram here. So this is a plot of the proof strength against the ultimate tensile strength. So the 2 points in the bottom left-hand corner are the as-deposited material in different directions. The 2 blue points are with 50 kilonewtons of rolling load. The triangle is the wrought material that's currently used and was tested for comparison. And then at the top right, you can see with a 75 kilonewton load, we have very high strength, around about 1080, and we have a proof strength of around about 980. And as I mentioned, it's fully isotropic. And if you look at the elongation, you can see that we now have an elongation of around about 13%. So this material is actually much better than the material they're currently using. So we're offering them, by them I mean the aerospace industry, we're offering them better properties, shorter lead times and lower cost. So as you could imagine, they're pretty interested in this. I haven't got time to go through all the mechanical properties of all those materials, so you can have a look on our website, which is wammat.com. There is a lot of information about mechanical properties and systems and so on. For titanium 6-4, there's notched and unnotched high cycle fatigue, fracture toughness, crack propagation, and also the interface behavior. So you deposit it on the wrought material, you need to understand what the effect of the properties is at that interface region. And similarly for the other titanium alloys. And then for the rest of the materials that I explained, you'll find the tensile properties mainly. And because we also have a lot of publications explaining what we do and explaining the academic reasoning behind it, so because of the copyright reasons, we have to put that behind a wall. But if you want to access the papers, you can log in as guest, and the password is guest. So that's a quick run through all the process and the material properties and everything that we do to get the properties we want. So I'm now going to talk a little bit more about the parts that we've manufactured. And my colleague, Jialo Ding, will come on to speak after I've spoken to talk much more about the systems and the software needed to build these parts. So this is the landing gear rig. This was the first variant that we made in steel. So we made this actually, and it seemed pretty good. So we went on to make the titanium version, and actually it was horrible. It had lots of undercuts, it had accumulated errors in layer height, we had cracking of the base plate, all sorts of issues. But you have to find out how to solve these problems, and this is the final part. So when we did the final part, you can see we have different deposition strategies. The geometry looks very different. We have no undercuts, and most importantly, we introduce compensation for changes in thermal field as you go around the part. In different areas of the part, you have different thermal mass. This changes the thermal field, so you get layer height errors, undercuts, and also defects if you don't do anything about that. Because we were, you probably know in the additive field, there's a huge community of people working on powders, but actually not many people work on wire-based techniques because it's more difficult, but also because you can't buy a commercial system. So we spend a lot of time getting industrial interest in the wire-based systems. And to do that, of course, we have to build lots of parts. So we have done that. So on the left, you can see 2 titanium parts. One is a spar system. The large turbine blade is about this high. This is a part that was made for GE Power and Water. It's a steam turbine blade. Next to it, you can see an equivalent titanium version. This is a lot of the parts we make are symmetric because this deals with the distortion issue. But also, if we have asymmetric parts, then we can manage that as well. This is a D-nose section for an Airbus aircraft. And you can see it's very asymmetric, but we have no distortion in the part. And you can see here, this is the part after it's been half machined. For some parts, we actually want to be able to build in many different directions. So to enable that, we have to introduce coordinate motion, whereby we build in different directions. So this enables us to build these bowl kind of structures, and also to build multi-hierarchy structures, whereby we can build in one direction, we rotate the part, and we build in another direction. So as will be explained by Jiao later, we have all the software that enables you to do this, and this software will be available as a commercial product later at the end of this year. So if you're thinking about doing wire-based additive manufacture, do come and talk to us about providing you the tools that will enable you to do that. And in fact, here we made this elbow structure as well. So this is typical kind of thing that's required for the oil and gas people. So how far have we got in terms of building parts and working towards real applications? This is probably the closest one that we have at the moment. This is a satellite propellant tank for we developed with Airbus. So it has these two halves, and you can see these flanges on either side of it. So the current manufacturing process is to take a 40mm thick forging, machine it all down to round about 1 millimeter thickness, and then weld them together. So this is incredibly expensive, as you could imagine. So we set about building this using the wire and arc process. So you can see a video. You can't see much at the moment because the plasma is very bright. You'll see more as it grows. So you can see that this is the bottom section, which is quite thick. You can see a picture of it here. So we build up the bottom section, then we move through to building the cylindrical thin wall section. Once we've done that, of course, we need to get it machined. So we then put it on a lathe and take it through and do final machining. And you can see once you've done the final machining, it looks just like any other metal part, basically. So I'll just let the video run a bit more so you can see the final part being built. So you can see we're continuously rotating the part and changing the build direction as we're doing this. We're also changing the build strategy to deal with different thickness of material that we're putting down. And of course, when we get to the end, we also rotate it round and put the flanges on. You can also see that we're building in a tent, so we don't use a full fixed enclosure. We tend to use this tent for this size of parts. So a question, of course, is if we do an X-ray CT, what can you see? Well, there is the X-ray CT of this part, and the answer is you can't see anything. So, of course, that's exactly what we want. So there are no defects in this part at all. And so on that basis, we then went forward to fully test it. And I must say that's as deposited. It's not hipped or anything like that. It's just as deposited. So here's the two halves welded together in the test rig. And this is the part after it's failed. So we did 75 cycles at 300 psi, which is the operating pressure. We then did 4 cycles at 1200 psi to test that out, and then we tested it to failure, and the failure mode was exactly as per the forging. So it was performed identically to the forging. So we get performance that's identical. What are the business benefits? The business benefits are 50% cost saving compared to the current process, the lead time reduced from years to weeks, and not only that, they can have a bespoke geometry every time. So whatever kind of flight or mission they have, we design the structure to be optimal for that mission. So this part is going forward for the qualification. This is another part that's going forward to qualification. This is a water tank for the Orion spacecraft. So you can see it's roughly 1.5 meters high, and again we had to use the coordinate motion for manufacture of this part. This is as deposited, and this is the machine part afterwards. So it looks rather beautiful, I would say. We're quite proud of this. So my colleague Jiao will talk a lot more about the systems and the software needed to build these kind of parts. I'm just going to say a little bit more whilst I finish about what we're doing going forward. So currently we're looking to supply commercial systems and software to run those systems, which will enable everyone else to build parts using this technology. and not just build the simple walls and cylinders. But we're continuing, so we've set up a new company to do that. There was a big problem because there's no supply chain for wire and arc additive systems. Getting a robot and a welder is not enough, so we'll be providing fully integrated systems with control and software to plan them and to run them, as will be explained later. So we want to roll that out to the community and enable everyone else to work in this area. In terms of the research that we're doing, we want to work on new materials and processes. So the current DAM processes use standard off-the-shelf equipment, welding equipment and welding wires. And of course, you can actually get much better performance if you design the system to do what you want it to do. And that's the big next step forward for us. So we want to do high build rate net shape deposition using specifically designed systems. Not only that, we're also using off-the-shelf wires. Now, when you do welding, you generally do one thermal cycle. When you do additive manufacture, you do several thermal cycles. The cooling rate is different, so you end up with a different microstructure. So the properties you get from welding wires are by no means optimum. So we want to tailor the design of the wire to match the thermal cycles that we have in the process. And this is surely going to be the next step forward, moving away from standard materials. We need a much greater science knowledge, including physics-based modeling. A lot of what we've done so far is based on some reasonable science, but not in-depth science. So a lot of people are getting a welder and a robot, or a laser and a robot and a powder. They deposit material, they have a look at what they get, and do a bit of analysis and publish a few papers. Really, we want to start with a much deeper understanding of the science that's required in this technology to take it forward to the next level. Physics-based qualification. So qualification is a major issue, and our approach is going to be to use a physics-based approach. If we try to use a standard welding approach, this will never work. You cannot possibly, in a particular part, we might have thousands of different process parameters. There is no way you're going to write a process specification for that. And there is no way you're going to go and do 100 different parts under the same conditions and take the statistically worst sample if you're only going to build 10 of them in the first place. So we have to have a different approach to qualification. Large area deposition, which Jiao will talk about, and also multi-process systems. 3D printing in space, so this is something that's very interesting. We've just built a new printer to go on the International Space Station, and that will be flying in 2021. Software, which you'll see later, and the commercialization. So just looking at the first challenges about doing high deposition rate. So you can do high deposition rate relatively easily. So this is using a tandem torch with 2 wires feeding into the same weld pool. And in this case, we achieved 10 kilos an hour. And in fact, we've been up to 15 kilos an hour with no defects. As long as you've got big parts, there's not really an issue in doing this. But as you can see, it's pretty rough and doesn't come out at a very nice shape. At the other end, if we take the wire and laser approach, so here you can see wire and laser deposition. And in fact, using wire and laser, you can get down to feature sizes just the same as laser powder, as long as you know how to control the wire properly. And you can see underneath a simple part. And if you look at a cross-section of this, you can see we get net shape deposition. So there are no surface waviness features. As long as you get the width correct, there is no requirement to machine it. And in this case as well, on the picture on the right, you can see we actually cold work this using peening, and by using that method, we're able to eliminate the large prior beta grains. So the challenge is, how do we get the high build rate deposition and the net shape precision all into one system? And that's what we'll be doing. And we're doing that through a new program that we have called NEWAM, which stands for New Wire Additive Manufacture, which is a 10 million program to be run in the UK. There are 4 academic partners, ourselves, Manchester, Strathclyde and Coventry universities. And some specific innovations that we're putting into this program to try and achieve these goals is what we call multi-energy source DEDAM. I can't say much about it at the moment because we're currently filing for a patent for this, but we believe this also has shaped feedstock material. We have a target of achieving 8 kilograms an hour net shape deposition of titanium. And if we're able to achieve that, then this, of course, is going to completely revolutionize the additive manufacture field. Included with that is the novel sensors for online process control. And what we want to achieve is in-process microstructure control. If we're able to measure the thermal conditions and solidification rate and so on during the deposition process, we're able to realistically control the microstructure that we're putting down. So we have to move away from this passive way of putting down lots of different walls and building different features, having a look at what we get, and so on and so forth. We really need to move to a proactive system whereby we know what we're going to get, we control the thermal cycle precisely, and therefore we achieve the microstructure that the industry people want. But for that, we need some very sophisticated novel sensors. I mentioned earlier about the co-development of materials and processes. So we're developing new materials and we're developing new processes. And we're not going to do them independently with each other. We're going to match the process to the materials, or we're going to match the materials to the process. And we're not materials people, we're process people. So we work with Manchester University, who are the process people. They tell us what the material requirements are, or what the material thermal process requirements are. We design the process accordingly. Or alternatively, we tell them this is the range that we can achieve in our processes, and then they design the materials to match the process. Online in-process NDT, of course, we cannot afford to build anything with holes in if we're going to put them on aircraft, so we have to have an inline quality control procedure, and we're working with Strathclyde University to include layer-by-layer inspection so that we know when we get to the end of building a part there are no holes in it. So we'll know that the material properties are correct, and we'll know there are no holes in it. So this is giving us the guaranteed structural integrity. The physics-based qualification, I mentioned about that. I don't have time to go into this, but the idea there is to achieve this low-cost, rapid qualification. And not forgetting, to do all this, we need lots of physics-based models. Currently, these are very lacking, so we need FEA and CFD for the process modeling. We need the solidification and microstructure models for the materials, acoustic behavior for the NDT, and then the crack behavior for the structural integrity. So not forgetting, we are a university, so we have to do some teaching as well, although the research is fun, of course. So we are setting up an MSc course on metal additive manufacture with our partner universities of Birmingham, Bremen, and Technico Lisboa. We will be providing the input on the wire-based processes, Birmingham on the powder-based processes, the Bremen on modelling and software, and Technico Lisboa on NDT. And we have some industry partners. So we're running a pilot course in 2018, and then the full launch of the course will be open in 2019. So that's everything I've got to say. Refer you back to our website. There is a lot more information than I've been able to get over to you in 40 minutes or so. But I hope you found it interesting, and encourage you to work on wire-based processes rather than powder-based processes. Thanks very much.
Muchas gracias, Dr. Williams. Thank you very much. Ahora vamos a pasar un pequeño break de solo 5 minutos, igual para poder darle la oportunidad a los ponentes que están en la otra sala, puedan ubicarse. Para poder ir a la otra sala, en la puerta se encuentra José Sakihama, en la puerta de mi mano izquierda, que lo puede acompañar para ir a la otra sala, y solo damos unos 5 minutos para poder empezar la siguiente ponencia. ¿Sí? Muchas gracias.